All right, let's get going here. So this afternoon, we're talking about advanced topics, about PV system code compliance. And we'll probably have people dribbling in through the afternoon because we have a couple other concurrent sessions. And then I guess the last session is not concurrent. So for those that are not heading to the airport or starting their beer 30 early, then we'll probably pick them up and then we'll finish up in time for happy hour. So, but how many people were here yesterday? So about a little over half of the folks. And so as we did yesterday, I'm going to go ahead and start by kind of getting some things out there. People have questions, maybe some things that you wanted to have answered yesterday you didn't feel were answered maybe completely or the way you wanted them to be, or new things that have come up, and open it up to the group to get some topics out there, and then we'll start diving into some issues. Who will be first? All right, we have any takers over here?
I was a little late yesterday, Bill.
All right.
Hear much peek ahead to 2017.
Right.
6947 and 70512.
We could easily take up our time talking about 2017 code, a lot to talk about, and we will be talking about that throughout today. And we saved a lot of that till today and kind of put it off from yesterday because it's more advanced topics. Many jurisdictions will not be dealing with the 2017 code until typically no earlier than 2018, except for Massachusetts and Colorado and a couple other jurisdictions. And then really about 2/3 of the country is into the 2017 code by January 2019. And so that's why right now, as of January 1st, 2016, about 2/3 of the jurisdictions in the United States are on the 2014 code. The most notable that is not, or the most notables that are not, would be California and New York, which are two extremely large markets for PV, and they defer longer. New York, much longer, in fact, sometimes. So, and California is typically 3 years behind because of their adoption of the building code process. So, so that's a little bit about, but we will be getting into 2017 code stuff since that's pretty much what I do. At least I've been doing that all fall long. So.
I don't know whether you did it, I wasn't in the last two sessions, but we're running into a lot of issues related to the hybrid systems with the AC coupled, and with dealing with, there's just a lot of things that the jurisdictions are having some issues with. We just got told the other day that they wanted us to have a separate disconnect for the battery to be exterior to the building.
Yikes.
Yeah, I don't think it's necessary.
It's not in the code, for sure.
So, anyway.
Yeah, there's a lot of reasons you don't want to do that, and yeah, I mean, education is kind of a mandatory thing, and unfortunately, not only do contractors have to know the code, but enforcers have to know the code, and it's not sufficient for people to make up rules. And authorities having jurisdiction do have some latitude on that, and that's one of our topics from yesterday is how to deal with AHJs, and that's a challenge in and of itself. But one of the reasons we work so hard on codes and standards is so that we have a very defensible position when an AHJ makes up a rule, because that happens often. You know, an AHJ make up a rule, and unless there's a very real safety reason that accompanies their rule and they can back it up, we have a code making process which we've been very involved with, The National Electrical Code's been around since 1984. We have a lot of activity in that area. It is the most active part of the code in the United States. Our code committee had more comments and more work done on it than any other part of the code by a long shot. And I think we have a very defensible position that we're working very hard to make sure things are done safely and adequately. To the tune that we do have a new article for energy storage systems, which is largely based on a lot of the good work that went into solar photovoltaic systems. So, so moving forward, we're always battling the situation where, you know, one of the challenges of solar is that now that we're popular, we've actually turned up on the radar screen of a lot of folks that never knew about us before. And a lot of these folks are regulators, and regulators regulate. And that's their job, and that's cool. And I don't have anything against regulators, work with them all the time. It's just that usually when, you know, sometimes you run into regulators that believe that you have not benefited from their immense understanding. And so they want to tell you what you've been doing wrong all along and what they think is correct. And but that's why our standards and our codes are a consensus process where everybody has a voice, everybody has a chance to weigh in, but then everybody votes on it too. And so we have a process where we, in the way the electrical code works is anybody can put in a proposal, then those proposals are reviewed by a panel. The panel makes decisions on those proposals and then puts it back out to the public. The public then reviews what the panel did on it, and the public is allowed to then comment upon what the panel did, and then the panel deliberates on the comments that they get from the public. And if they get a ton of comments on a particular area, then they have to figure out, okay, what's right and what's wrong. But if they get one whack job in left field, banging their pot, it's like, no, nobody else believes that. So bang your pot, but don't be changing the code. What are some other questions? Over here, Richard.
I have questions on grounding and bonding, and
Okay.
kind of one thing that's always toyed with me, and it is like the old in-phase M215s originally, before they had an integrated ground, how that internal trunk cable wire, what was that? Was it just an equipment ground for the internal components, or was it also a system ground? Because you had to have an equipment ground on the outside of the inverter or to the rails or something before that. Now you don't. And I think in understanding that would understand all the things that maybe just we kind of gloss over as maybe, oh, we just ground it. And there's a lot of different groundings going on. And I don't know. Maybe this isn't the topic for that. Maybe everybody else understands that. But, you know, I just would just try to.
It's a good case in point of why we do things. So we'll go through that.
Yeah, I'm going to just touch on grounding. I know there were some changes. I deal in two different jurisdictions, 2011 and 2014, so I know there were some changes to 2014. So if it's possible to touch on those new requirements, and then also addressing ground mounts where the racking system could be used. I think it's 69056, but I might have the wrong number, or 54, where the racking system can be used as a grounding. The racking structure can be used as a grounding system, and I'll get an inspector who still wants a ground rod, even though I've got 10 concrete tubes 5 feet deep with steel tubes in them.
That's a different issue. So, yeah, you've got about 3 or 4 different issues we can cover in that, and hopefully between the two of those, we'll figure that all out.
The rapid shutdown, they're starting to enforce that where we're at.
Uh-huh. What jurisdiction you in? Idaho?
Understanding that, do we need to shut down the battery portion of that? Or, I mean, I've read an article that says you got to shut all that down, and I don't know where.
I wrote one that says that. You might have read it.
Solar,
Solar Pro magazine, maybe? There you go. There you go. I am the author of that. Yeah, the way it was written for the 2014 code, it just says PV system conductors, period, full stop. And so the way the 2014 code is written, batteries are considered part of the PV system. 2017 code, we remove batteries from the PV system. So we're very, very clear in the 2017 code that a battery is an energy storage system. It is a separate animal. It is not part of a PV system. Okay, the PV system generates PV power and could include the interactive inverter if there's no other things going on. But the way to think about it, and in fact, we'll just say PV systems versus other systems, we'll look at where the PV system disconnecting means is. And it's a really, really important distinction that we had to nail at this code cycle because for the last 25 years, PV systems have been batteries, they've been PV modules, they've been load circuits, all included. And we call that a PV system. And it's like, time out, guys. It's getting way too complicated to be saying that anymore. Because and hydro, where does hydro fit? And wind, and no. These are all different systems. Now you could have a multifunctional inverter that has 10 different power sources coming into it. And that's okay. But each one of those power sources have to have a separate disconnecting means because each one is a separate power source. Okay? And so you may have one brain that's doing all kinds of different things, but at the heart of a PV system is photovoltaic modules producing power when the sun's out, and then it could interface with all kinds of different systems out there. And so from a code point of view, we've gotten ourselves into such a tizzy in 690 with all these other provisions for batteries and loads and things like that, that it's created a lot of problems for enforcement and for contractors. And so we said, this is the time to demarcate this stuff, and here's how we do it. So we'll show you some diagrams because it really took diagrams to show what we're talking about with multimodal inverters and everything else and how those things work. And this was a concept change for the whole PV industry. And I'm the one that drove the truck on this, but it's really necessary that we keep these things compartmentalized for the purposes of codes and standards, and then figure out how we bring them all together when we have these master units that can do 20 different things. Okay, so that's a good one. Rapid shutdown's a good one.
Along the point of rapid shutdown, if we expand a little bit further onto the commercial side, a lot of the roof mount jobs are complying with the rapid shutdown by placing the inverters on the roof. In the situations where the inverters are not on the roof, is there a need for capacitor discharge for those inverters? Because I don't believe currently there is a solution for that.
Well, not all inverters have a lot of input capacitance on their input circuits, so some might not need it. Old school inverters from a couple years ago, almost all of them needed it. So input capacitance was very common on typical SMA inverters from 5 years ago. Now with your non-isolated DC to DC converter input inverters, there's very little capacitance on the input, and so some inverters might comply, some might not. And so where we're going with all that is we have standards written, and that standard is going to get voted on the next month or so, and then that'll be rolled out, and inverters will become rapid shutdown compliant on their input circuit. And either they're going to do that by the fact that they pass the tests, or they're going to do that by having to have contactors or something like that to shut off their capacitors. So to do it today, we would probably have to have capacitors on a lot of units. Contactors on a lot of units if we want to do them separately. But if we're doing commercial installs on flat roofs, I would highly recommend putting the inverters on the roof. Highly. within, close range of the array. Far easier to do it, and we have lots of products that can do that right now.
So anticipating the new technologies, if you could address, there's going to be, like for example, the Tesla battery pack mated with the inverter. There's not going to be specific language necessarily in the code that addresses that, but there is also a standard that says if it's a UL listed component system that is put into service for the function it was intended, right? Could you just talk about that language?
No, the code is actually very specific now, far more specific than it was before about energy storage systems. It's got its own article. So we have Article 706, and a listed battery unit would certainly be one method of compliance and probably the most straightforward method of compliance for smaller systems. As you get into larger systems, the dynamics of the system may be such that it needs to be engineered, and so there's another category for engineered systems and all, but the listing process will be covering things like the Powerwall-esque products of the world. Those will all be listed products. So you're not going to see somebody building a lithium-ion battery for a house. Not going to happen. It's going to be a listed package from one end to the other, because you cannot mix lithium-ion without a very strict battery management system that is absolutely engineered for that battery. There's end of story. And we've seen people try to do it, and it's scary. So there's things that certain technologies and certain chemistries we've lived with for a long time, like lead acid. We understand how to deal with it, and we understand how to do overcurrent protection. You can't buy a listed battery, a listed lead acid battery. It doesn't exist, and it will never exist from the standpoint of a cell, because that's not the way it's going to be certified. But we're allowed to take flooded batteries, and there is equipment out there that we can work with, or we can take AGM batteries, we can take different style batteries, and we've been doing that for years in the code, and 690's had a fair amount of direction in that. And the information that was in 690 didn't go nowhere, it went to Article 706, all of it. So basically all of 690's Part 7 went into 706, and then all of the vast majority of 480 went into 706. 480 went away, and so now we have a new energy storage system.
Right, but my question is, don't you anticipate, because I've seen it, okay, you get inspectors, they're finally getting on board with solar.
Mm-hmm.
They've seen grid tie.
Mm-hmm.
They've seen grid tie battery backup.
Okay.
They've seen off-grid.
Yeah.
Okay, and now we potentially have these new technologies, and they go, what's this?
You mean like a lithium-ion battery or something like that?
Like the mating of the solar edge and the lithium and the Tesla Powerwall.
Well, like I said, I think that's a pretty much of a slam dunk in my view. I mean, sure, you're going to get people have questions about it, but you're going to have a listed battery pack with a listed battery management system. You got a listed inverter. You got installation instructions on how to put together. That's way better than what we had even 5 years ago. So I think it's actually, we're moving in the right direction. Are we going to have hiccups along the way? Sure. And if other companies don't have it together in their listing process, and that it's not a listed package, then I think there are going to be a lot of questions. And then we're going to have some old questions being brought up again about the old lead-acid battery style systems that we used to do all the time, because part of that work that we did was there wasn't 100% information in the code on how to do it. So there was approval of the local jurisdiction that had to be applied. And we had a lot of jurisdictions that became very, very adept and very familiar with battery systems, especially here in California. We probably had over 2,000 battery systems in 1999 in the state of California, 2,000. And so everybody said, oh, battery storage is a new thing. It's not even close to new. And it's not even close to new in grid tie applications. But a lot of the folks that were around back in 1999 are no longer, they're retired, and so they're no longer around. And so There is an education process that has to happen. And actually what's going to happen because of products like the Powerwall and other listed packages, it's really going to force the lead acid market to probably have to step up a little bit, because the inspector is actually going to look at the listed package and say, I'm good with that, but what about you guys? You guys are just, looks like you got a bunch of car batteries sitting there. That sounds a little scary to me, you know, what do I do with that? And so I think that's going to actually garner some questions and question marks. Any other questions before we get jumping in here?
I was going to say 2 things that we've seen lately, maybe you could touch on. Number one would be with on battery systems with the arc fault protection. And so we're seeing some industry stuff come out now. Outback seems to have something there, but up to this point we haven't been doing anything there, and they haven't. None of the AHJs have been requiring that. So, and we still don't have.
Not a code requirement, so it's not a code requirement, but a manufacturer could do arc fault protection.
On battery systems, but arc fault on the PV.
Ah, that's a different story. So.
And then the other thing we've had was on battery-based systems with the emergency panel, or your critical loads panel, shutting that down.
Shutting off the critical loads panel. For rapid shutdown, or for what other for what reason?
Just disconnecting the AC.
Okay.
So if we have a critical loads panel coming off our battery system, and we're not shutting that down with our service disconnect for the house.
Right.
So we're looking at doing that off a rapid shutdown, just shutting off the inverter, but I don't know if there's another way in the code that we could address that. Or.
Well, there's a section of the code that not a lot of people know about, but Article 702 is optional standby systems. And that's been in the code forever, and it's got requirements, and we routinely would call upon Article 702 back in the late 90s and early 2000s with battery systems, because it talks about where you put disconnects and how you talk about them and things like that. And so we can talk a little bit about that as well.
I'm just going to be listening since you're kind of taking.
Oh, all right.
So, interested in comments on cable management.
Okay.
Anything related to it that we can think of. Wire splices. And then the last item would be anything related to underperformance or common failures or issues.
Okay.
So that's kind of.
All right.
Thanks.
You hit limitations on supply side and load side connections.
All right. We'll be talking about that for sure. All right. Well, let's dive in. We can certainly answer questions as we go, but this is a nice little thing to get us started. And we're going to probably dive in the deep end in Article 705, because that's where a lot of the questions are actually related to some of that stuff. The grounding and bonding questions are really good questions, and I'm just trying to think of some materials that I have that can easily discuss these things. We talked a little bit about it yesterday, So probably one of the best things, just kind of hit that, and maybe we'll move on to some other things, is that as we talked about yesterday, we have system grounding and we have equipment grounding, two very different animals. We do them for very different reasons, both of which include a connection to the grounding electrode system. So every electrical system has a grounding electrode system. That electrode system could be as simple as a single driven ground rod, and could be as complex as UFR grounds, as building steel, all kinds of things can be part of a grounding electrode system. And so both a system ground, which is going to be a connection from conductor, a current carrying conductor to earth, and an equipment grounding conductor, which is not a current carrying conductor, but is actually connecting bonded exposed metal to earth, get to this grounding electrode system. The specifics of a microinverter, since that is a great example of a situation that was kind of complex and didn't make a lot of sense from day one. My very first meeting with Enphase, when they were just starting as a company, sat down with one of the founders of the company, and they started talking about their product. And my very first question was, why are you grounding your inverter? You know, why are you doing a system ground on your inverter? Because I said, what that does is that means you got to bring a DC grounding electrode conductor up to the darn inverter, and the inverter is way up on the roof. It's not a big deal when it's down at ground level, but it's a really big deal when it's up on the roof. It's a pain in the neck. And so, you know, we talked about that, and they said, well, this is where we are now, and, you know, in the near future, we're going to come out with a product. And so they came out with the integral ground system. Unfortunately, that created as much confusion in the name of it as anything, because the DC circuit is not grounded in that. It's just an equipment grounding conductor. And it does provide reference for different things in their unit and stuff like that. But the fact is that with that particular product, they don't have a need for a DC grounding electrode conductor. And so the equipment grounding conductor is sufficient. It's sufficient for the inverter, could be sufficient for the module as well. And it's certainly possible with the bonding of the module and the frames to actually ground everything through the cable. And there's nothing wrong with that. In fact, that's obviously where you want to go. You want something to be very simple and clean so you don't have a bunch of wires hanging all over the place. The days of bare copper conductors climbing around on a PV array are very numbered, and they will be gone within 5 years. We will never see that again, thank God. So anyway, so we're talking about grounding. The 2014 code put in some additional information which basically just makes it clear that the AC equipment grounding conductor can be used as the reference for ground fault detection. It's also capable of being the conductor that's used to connect the DC equipment grounding conductor down into our service equipment, which is connected to earth. So if you're looking at an equipment grounding conductor in general, you have the DC equipment grounding conductor, which is bonding the module frames and the rails and all that kind of stuff up on the roof, any metal raceways, metal boxes, all that kind of stuff. And then the equipment grounding conductor is taking that along with the circuit conductors, which is what 690.43 says along with, down to the place where that circuit terminates. Where does the DC circuit terminate in most of our PV systems? It terminates at the inverter, at the DC input of the inverter. So that's the termination of the DC equipment grounding conductor, but it has to connect to earth somewhere, right? Okay, so it's not sufficient to stop there. It has to get to the grounding electrode conductor, or it has, you know, which goes to the grounding electrode. So how does it get to the grounding electrode conductor? Well, we could install a grounding electrode conductor from the inverter directly to ground, but certainly a lot simpler thing is that the fact is this piece of equipment has an AC equipment grounding conductor. That AC equipment grounding conductor on a grid-tied system is going to be tied into the service equipment somewhere, either a sub-panel or the main service panel of the building, of the house. And so the termination of that equipment grounding conductor forms the fully acceptable path all the way to the grounding electrode conductor, which is connected to earth. And so that finishes the story for us, which is the use of essentially the AC equipment grounding conductor to make it back to earth. And this is not any different. In fact, a good analogy that if you run into a situation where you're trying to explain this to an AHJ and they're just not getting it, Think of an inverter and a PV system like a separately derived AC system off of a transformer. So let's say we've got just to use some analogies for you, we got a 480 volt three-phase service to a building like this, and then we run out of that into a 208 transformer. The 208 transformer goes to our 120 volt loads and stuff like that, and lower voltage stuff in the building. Well, that particular transformer is typically grounded to building steel, but it's also grounded through the equipment grounding conductor back to the service panel that serves the breaker that feeds that transformer. And so that equipment grounding conductor is actually what makes it all the way back over to the main service. And so we're doing the same thing with that whole process. And once people see it that way, then they go, oh, okay, we're okay. We're not stopping the grounding conductor and then leaving it hanging out, dangling, in the breeze. So a lot of this trouble that we've run into with grounding has been that we kind of walked down this road, we talked about this a little bit yesterday, where we ended up calling a PV system a solidly grounded system, and it just ain't so. We haven't done solidly grounded PV systems since the late 90s. It's very rare to see one. Occasionally you see them with battery-based systems, but they're very rare even nowadays. Everything's got ground fault detectors that lift grounds, and those things are not solidly grounded by any stretch of the imagination. These are essentially reference grounded systems, or what we call functionally grounded systems. So we had to change the nomenclature of the code as well, because that was creating half of the problems that we're seeing in the field, which is causing a lot of this concern with the HJs. The HJs are trying to apply their knowledge of solidly grounded AC systems, which they know about and work with every day, and every house has a solidly grounded AC system. You got a neutral wire. That neutral wire is connected directly to the grounding bus, which is connected directly to the earth, and there is no fuses, no nothing in that circuit. That thing is solidly grounded. But that's not at all the way our PV systems are set up. In fact, as we talked about a little bit yesterday, the real danger with the way we've done things in the PV world is that when we have a ground fault, which definitely do happen, when those ground faults occur, especially if those happen on the ungrounded conductor, which is the most common ground faults that we get, it's going to cause the positive conductor to go to earth potential, and then it's going to cause the negative conductor to go to minus whatever the open circuit voltage of the array is, which is going to be 400, 500, 600 volts, or even higher with a 1,000 volt system. Unfortunately, the problem that creates for us is that previously grounded conductor, which now has become ungrounded, is bolted at every connection in our system, okay? Which means that in order to work on it, we actually have to work on it live or work on it at night. There is no two options on that case. And we are going to hurt and kill people with that kind of scenario. It's not a good situation. So 2017 code, in changing the nomenclature, we also changed the methodology, which is requiring disconnecting means on PV systems to disconnect both the positive and the negative conductor in all cases when we're controlling equipment, because we cannot have bolted connections that are live. The way the 2014 code and previous is set up is we have 3 or 4 labels that are required to warn people that a ground faulted system can kill you. And that's not the right way to operate. And the reason that folks were so adamant that we not put a switch leg in the grounded conductor was because we were assuming that we were talking about a solidly grounded system. And the basic rule with a solidly grounded system is you generally don't put a switch in the grounded conductor, because that grounded conductor is used to reference the circuit to earth and things like that, and if you lift that, you might create some kind of an issue. However, just a little aside there, the electrical code allows us to break our grounded conductor provided that we break all conductors simultaneously, okay? So there is no prohibition in the code that says you can't break the grounded conductor. It requires you to break all conductors simultaneously if you do break the grounded conductor, so that there's no source of supply through any of the other conductors. So anyway, that's just a little bit of how we're dealing with things, and let's just save this for a second. And we'll save it, not there. You dorks. Whatever, we'll put it right there. Thank you. All right. So today is advanced topics. We talked about basics yesterday. IV curve, got to know it. Changes current and voltage with temperature and irradiance. But we're going to jump down to the changes in the code. So we talked about some of the changes in the 2011 code, which was routing identification, arc fault detection, did a little reorganization, moving some things into 705, which is why we have to talk about 705 now. And then in the 2014 code, we got specific about how to detect ground faults, raised our voltage levels for low voltage up to 1,000, changed some of the arc fault detection requirements for ground mount, added ground mount requirements. So gentleman asking about battery-based systems with arc fault detection. Yeah, well, the PV part of it, the array, is required to have arc fault detection, period, end of discussion, full stop. So you either have to have a charge controller that's got arc fault detection in it, or you got to have an inverter and do an AC coupled system. There are really, I don't know, is there any other option you can think of? Or you'd have to have a separate arc fault device. And good luck on that, because they're just not out there. So yeah, so to comply with the code, if you're going to do a code approved system that's under the 2011 code, okay, then it would have to have arc fault detection on the array. And whether it helps with the battery system or not is irrelevant. It doesn't matter. Now, an arc fault detector on a charge controller might or might not do anything on the battery side of the equation. But the array still needs it. We're going to talk about rapid shutdown, which started in 2014 as the conductor's leaving the array. In the 2017, we'll actually cover shutting down within the array itself, or improving the, reducing the shock hazard is really the key concept there. We talked about combiner disconnects yesterday and things like that. Cable tray, multi-jacketed cable, multi-conductor cable, metal jacketed cable, all fun stuff. And then we're going to go into the details in 705.12 because there was so much that went on in the, hold on a sec, that went on in the 2014 code. And then we have some more information about line side connections and single phase inverters on three phases.
Back to the arc fault on ground mount arrays, just briefly, is there any size limitations? So small telecom arrays with 2 panels to a small PWM controller? I mean, or maybe a small repeater for a Wi-Fi signal that somebody puts up at a summer camp or something like that. Is there any size limitations on that arc fault protection required for all PV arrays?
It's a voltage limitation, 80 volts or less. Yeah. So most of your small systems would be at lower voltage.
Thank you.
Can I ask you a question about the combiners, maybe a definition thing? We don't combine hardly anymore at all, but we often go from PV wire to THHN in a box.
Right.
Is that box considered a combiner or not? We don't combine.
Not if the circuits are not being combined. And here's kind of an interesting story. Yeah, the definition of a combiner is a little bit loose in the code. If you take 2 strings of modules and you connect them together, all right, and then you terminate them at an inverter, is that 2 source circuits or 1 source circuit?
2 sources. One by fuse, you have to fuse it.
So here's the deal. The code talks about PV source circuits. And a source circuit could include parallel series arrangements. And essentially, that source circuit then gets combined with other source circuits that then, after the combining process, become a PV output circuit. So given the way the code is written, we don't have the term string. It doesn't exist in the code. Okay? So, and a source circuit is not a single string of modules. A source circuit, in fact, we should read the definition. It's always healthy to read the code. Let's bring it up. And these are the kind of things you have to do when you're working on the code. Is you got okay, this is what it says. This is what we're working on. And so a source circuit. Circuits between modules and from modules to a common connection point of the DC system. Well, I can drive large trucks through that. And then a PV output circuit are circuits between the PV source circuits and the inverter. Okay? So a common connection point, I could define that just about anywhere, anytime. And so in history, we've had source circuits that had multiple parallel and series circuits in them. In fact, in the old thin film arrays, we would have 5 strings in parallel with each other as one source circuit. Okay? And so there might be diodes in the array, there might be all kinds of different things, but that's the way the code was written, and it was written around that. So when we get to a combiner box, then we go, okay, well, what is a combiner box? Because that's kind of a little different animal. So we have a direct current combiner, a device used in the PV source and output circuits to combine 2 or more DC inputs and provide 1 DC output. Okay? So where the ambiguity comes is if I'm just wire nutting together 2 strings and then coming out as 1 string and everything is fully rated for the current that can handle it, is it 2 source circuits or 1 source circuit? And I would have to say it's not clear. And so since it's not clear, that can create an issue where one guy says, well, I believe it's this, and another guy says, I believe it's that. But I don't believe we can be super dogmatic about it. That's the first time direct currents combiner made it into the code, 2014 code. And we did talk about this issue. It's like, is that Y connector, let's say you had a Y connector for plugs. Is that Y connector a combiner? It's combining 2 circuits, but it's not a combiner from the perspective of a whole bunch of fuses and terminals and that kind of thing, which is a DC combiner is the analogy of an AC distribution box, right? So an AC distribution box just takes AC in and distributes it to a bunch of different branches. And what we're doing is we're taking a bunch of branches and we're combining them in, and then we're going into one trunk, going back the other direction. But the fundamental purpose of that box is identical to the AC box.
There's like a difference between a breaker panel and a junction box.
Correct. So this is like a junction box. Would be a great way to maybe that would help in your working with the HJs. This is a junction. It's not a combiner in that sense of the word. But we're probably going to have to add more words as we go forward because we're still going to have people kind of get tripped up on that. Okay, so that's just a little bit more on the 2014 code. There's a requirement for separation of AC and DC circuits, things like that. We rewrote 13 through 17. And I think that covers it for that. We'll jump into the 2017 code now. Is there a question back over here?
Your comment on the previous screen there about 690.7 1,000-volt systems for other than residential rooftop systems. Yeah. Does the code actually say residential rooftop? Because AHJs are saying no, it says residential, not residential rooftop, meaning you can't use 1,000-volt on ground mount.
And that's not true. So you got to read the code. So let's go back and read the code. Because it's so interesting. Everyone knows that. Okay, so here we are, 690.7. It's in the preamble. Now, some of this has been cleaned up since then, but we'll just go with what it currently says. Let's see, that's for lowest expected ambient temperature. I think it's over here and keep on going down. Here we are. Source and output circuits. In 1 and 2 family dwellings, source and output circuits that do not include lamp holders, fixtures, or receptacles shall be permitted to have a maximum voltage of PV voltage of 600 volts, up to 600 volts. Other installations with a maximum PV system voltage over 1,000 volts shall comply with that. Okay, so it doesn't talk about what's in between, and it says 1 and 2 family dwellings, PV source and output circuits. And here's an interesting little ditty. Everybody's familiar with grid-tied systems that were, that's the rule of the road today. Well, 20 years ago, grid-tied systems were almost unheard of. The vast majority of systems were off-grid systems. They were standalone systems. And what this particular clause is talking about, look what it says. It's talking about if it doesn't include lamp holders or fixtures or receptacles, which means it's a hardwired system in a dwelling, it's allowed to go up to 600 volts. Now, if it's got receptacles and stuff like that, then it's limited to 150 volts to ground. So if we're bringing the DC conductors inside or in and around the building, then 600 volts is your max. There's no question about that. But if you have your inverter out at an array that's separated from the house never sees a bit of that, okay? And I don't believe that this limits. This is a 1 and 2 family dwelling. Now, there are definitely there are people that disagree on that. So there was a big case in southern New Jersey, and this guy was like he was an executive for the utility, and it had a 480 service to the house, okay, which is its own little different thing, because that's not normal to start with. And so they used 480 volt inverters, which had a 1,000 volt input on a ground mounted system that was 200 feet from the house. And the local jurisdiction nixed it, would not allow. So they contacted me, they contacted John Wiles, we both agreed, said, hey, there's no stipulation in the code that says you can't do it outside of the house. You just can't bring the conductors into the house. And they still wouldn't buy it. It's like, okay, that's fine. You're wrong, but you're the jurisdiction. So yeah, there's no limitation on voltage if you're not bringing the conductors into the house. And that's true of the electrical code in general. The stipulations on the code have to do, there's a big difference from being in or on a building versus separated from a building. The code's very different in how it treats those two systems. And so, like I said, you can have a power source away from a building, and I don't know that there's any voltage limitation whatsoever on that. But you're going to have listed products. Good luck with anything over 1,500 volts that's listed. The highest voltage stuff that we have in the United States right now is 1,500 volts. So that in and of itself is going to create a barrier. 1,500 volts is going to be your max for the vast majority of anything that's in the built environment. But other than that, they're not correct. So, and it talks about access to other than qualified persons and stuff like that. So, anyway, let's dive back into the 2017 code, since that's got some interesting stuff. So, in the 2017 code, I mentioned that we have this new Article 706 on energy storage systems. The leadership that essentially oversee the development of the National Electrical Code are very well aware that lots of things are changing. So that's why we have several new articles in the code. Comment in the back?
What is the definition of a qualified person?
Got to read the code. It's in Article 100. And is it an enforceable thing? And the answer is probably not. But it is. It's in the code, and we can, you know, quite frankly, it was something that was crammed down our throats to put it in Article 690. But the reality is that you can't work on electricity unless you have the necessary qualifications to do whatever you're working on to start with. That's kind of a generic thing in the code. Regardless of the application or whatever, you got to know what you're doing. And that's basically what Article 100 says, that you've received the training, and understand the safety hazards, da 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 da. That's what it talks about in Article 100. Article 691 was something that we put together last summer in response to the fact that we have a lot of large-scale plants going on in the United States, and these large-scale electrical supply stations are getting inspected by local jurisdictions, whereas local jurisdictions don't step foot on the vast majority of any other electrical power system in the United States as far as a power station. It's either, it's normally been considered utility property, and so the code is very clear that if it's owned by the utility, that the local jurisdiction has no jurisdiction over that. So that's been a clear demarcation from day one. What's gotten fuzzy is the fact that we could have a PV system, and let's just say, for instance, that the utility did build the PV system, and they build this very large plant. Let's say it's a 50 megawatt plant, and then their leadership decides that they want to spin off this plant and sell it to a third party. So now a third party buys the plant, and now you touch a bolt in that plant, and you've got to bring it under the National Electrical Code, when it was clearly outside the National Electrical Code before. And so we have this problem that utility ownership does not do a good job of delineating one way or another on how you should treat a PV system. And so we put together an article that talks about the engineering reports that are necessary and the things that have to be addressed in the development of a utility scale style or large scale power plant that would often take exception to things that are in Article 690. Because Article 690 was written initially for off-grid homes and for small residential applications. That's where it started back in the 80s, and it is now morphed into something where it's actually being used for large-scale 100 to even 500 megawatt plants, the largest plants in the world, not far from here, 550 megawatts. And it really does not make sense to be applying Article 690 for large-scale plants. So that's why we have 691. We'll get into 690.1 about the signs that clarifying PV system disconnect. In fact, maybe I can bring that up right now. Let's see, I should have.
And it is large-scale defined, like greater than
5 megawatts. No smaller than 5 megawatts.
5 megawatts, okay.
We had to pick a number, and we knew that whatever number we picked, everybody was going to talk about that, and it was a great way to focus people's attention on something that didn't matter. Because the number makes no difference. It really doesn't. But we didn't want to make it so low that a lot of different things would apply. So 5 megawatts. Some wanted 20 megawatts, some wanted 1 megawatt, and 5 seems like a really good number for now. Let me see. Let me get to right here. Hold this. Oh, there are all kinds of transformer sizes. As far as standard, I don't know about that. Wait a minute. sorry. I'm going to bring up, there it is. Okay, so let's talk about what the code says right now. So the 2017 code defines this thing called a PV system disconnecting means. In this case, a PV system disconnect would be the noun. And so what we're going to say is, so the way to think about what a PV system disconnect is that if we're standing at the PV system disconnect and we look toward the solar panels, I'll use panels instead of modules, but we all know they're modules, but everybody else in the world calls them panels. Okay, so we look toward the array, and there is nothing but solar PV system over there. If we look away from the array, we see other stuff. Okay, so think about it. So everything, as we're looking toward the array, everything that's in that electrical system is specific to the PV system. The modules, it's got combiner boxes, it's got disconnects, it's got junction boxes, it's got cabling, it's got whatever it's got to have, up to that disconnecting means. When I turn that disconnecting means off, it separates the PV system from all other conductors in the building, period. Now, what it's not going to separate are things like equipment grounding conductors. You don't mess with those. Those are always connected to earth. Okay, but it separates all other conductors from the building. Okay, so if I turn off the PV system, I know that that PV system is isolated from the building conductors. There are no load conductors whatsoever in the building attached in any way, shape, or form to that PV system. Okay. And if I have a battery, the battery is on the non-array side of that PV system disconnecting means. Okay, so the very simplest system is going to be right up here. And let's make this bigger here. So that's the system that is by the millions going in today. It's the utility interactive inverter. There's your PV system disconnect, and then it goes into the electric production and distribution network, which is a fancy name for what's ever connected to the utility. Okay. An AC module system. Okay, well, then that's a bunch of AC modules. And all that stuff, there's no batteries in here. Okay, so as soon as you start interjecting batteries in here, and let's just say this is an N-phase system that has N-phase AC modules in it, that is not going to have any batteries in here. Those batteries are going to be over here. All right, that is on the other side of the PV system disconnecting means. Now let's talk about a DC coupled system. A DC coupled system can have any number of DC power sources, including the PV array. And of course, we have an energy storage system. That energy storage system has an energy storage system disconnecting means. Okay? The PV power source has a PV system disconnect. This is where the PV system stops. And this is a huge change from 2014 to 2017. All right, it's a very fundamental change. DC load circuits that have historically been treated as part of a PV system. What a craziness. We just did what we did because we had to. Those used to be part of a PV system. And they were considered as part of the PV system. Receptacles, hardwired systems, the whole thing. Craziness. They're not part of a PV system. They're loads. The code has all kinds of rules about loads, and they have nothing to do with PV. So that's, and then we could have a multimodal inverter. This multimodal inverter could have numerous DC inputs. As you can see here, we've got just an energy storage system in here, but we've got the PV system, we've got an energy storage system, we could also have a wind system, we could have a hydro system. All those things are great inputs, each one of them requiring their own separate disconnecting means, so we can isolate and work on each system independently if we choose to do so. All right? And if we ever have to shut down the DC input of our multimodal inverter, we have to go around and shut down each and every input, each and every power source. And the code's very clear about that as well. All right, so typically, and as we see here at the expo, when you have multiple inputs here, you're going to want to have the disconnecting means for all of those inputs very close to your multimodal inverter, because the code requires you to be able to de-energize all energy sources into a piece of equipment, and it has to be within sight or at the equipment. okay? So you can't have these things, you can't have a PV system disconnect that's 100 yards from your multimodal inverter and say, hey, I got one out there. That's not acceptable. It's got to be at the inverter where you might have to work on the piece of equipment, okay? And which is why we have some great pieces of equipment that we've been using for years that do this kind of stuff every day. And then we have on the AC output of this, there's two AC outputs of a multimodal inverter typically, correct? The reason we call it a multimodal inverter is one mode is connected in a grid-connected mode, and the other mode is a standalone mode, right? And so what we have is we have the interactive system disconnect, which goes to the utility system, or it could go to other electrical distribution networks, because it might not be the utility. It could be a microgrid. It could be all kinds of different things. That's why we use this more generic term. And then we have the optional standby loads, or the standalone loads that this thing is serving. And that's covered by the load section of the code. Does that make sense? All right, so let's talk about AC coupled. Same thing here. Very simple. We've got an interactive inverter. And since, again, we have to talk about that disconnecting means has to separate us from all other circuits of other systems, the PV system disconnect goes on the output of the interactive inverter. Now, we could have multiple interactive inverters, could we not, in an AC coupled system? So each one of those would be a PV system disconnecting means. All right? And the code allows us to have up to 6 PV system disconnecting means in one system, and they would have to be grouped and connected together, or grouped together, is the way they said. So here's our optional standby loads. So it can't be on this side of the optional standby loads, because then the loads would be part of the PV system, and that's not allowed anymore. And then your energy storage system is the only thing on the DC side of this particular example. Now, you can have a DC coupled and an AC coupled system. We're not going to go there. This is just showing different iterations. The fact that we were able to get this many diagrams into the code, new diagrams, is a miracle. Just trust me on that. So it's very good that we have these things. And here's your basic standalone system. This is a DC coupled standalone system where the PV system disconnect is before the energy storage system. It looks very much like the multimodal system, except it doesn't have the utility interconnection. And so the point of demarcation is the PV system disconnect. Any questions on that? Is that clear? Okay.
So, on one of those diagrams, on most of them, the PV system disconnect is on the DC side of the inverter, but on the AC coupled system, you had it on the AC side of the inverter.
Correct. Absolutely. Because the point is that until we introduce the loads, everything about this system is PV. The interactive inverter is critical for the PV system to contribute to the AC coupled system, is it not? You can't have an AC coupled system with a DC output array, because that's not AC, right? So the interactive inverter here is interacting not with the grid, it's interacting with the multimodal system, right? Which is why we changed the term from utility interactive inverter to just interactive inverter. That was a very calculated change, because our interactive inverters are no longer just interacting with the grid. They're interacting with other inverters. They're interacting with both current source inverters and voltage source inverters, and loads and everything else. And so, and they may have to communicate with one another. There may actually be communications between the multimodal inverter and the interactive inverter. There's all kinds of different configurations that may be necessary. But what is clear is that this PV system disconnecting means controls everything that is PV related and nothing else. And so you slide that disconnect to wherever you have to do to stop where the PV system starts. If that makes any sense.
On the standalone, I didn't
say the charge controller would be on the PV side, I guess, not the other side?
Depends what the charge controller is doing, but I would say in general, yes. Okay, so if the charge controller, yeah, I'd say in any case that I can think of, the charge controller would be in the PV system. Particularly if it's doing arc fault detection, doing ground fault detection, all that kind of stuff. That's all requirements of the PV system. Now here's where it gets a little bit funky, is you could have a multimodal inverter that is performing some of the required functions of a PV array. Okay, so let's just say, for instance, you had a multimodal inverter, and inside that you're doing your ground fault detection and arc fault detection somehow. The box itself, the funny thing is the box itself may not be the delineating point of where the PV system ends, because you've got all kinds of switches in there and things like that. So it's really more about the electrical part of the system, which could be included in this box that is controlling all these different multimodal systems and all. At the end of the day, the code says you got to have arc fault detection, and the code says you got to have ground fault detection. Now, whether that arc fault detection covers more than the PV array or not, or the ground fault detection protects more than the PV system or not, it doesn't matter. As long as it does the PV array, you're code compliant. So, as I said before, you could have an arc fault detector or a ground fault detector. Our old battery-based ground fault detectors did a great job of detecting ground faults on the battery, right? If you had a battery ground fault, that sucker's going to go, because that's your only connection to earth, and current has to come back up through that thing to finish the circuit. So you'd pop your ground fault detector if you had a ground fault in your battery. That was not the primary intention, nor was it the requirement of the code, but it certainly worked for that. And the same thing could be true of arc fault detecting. Okay, any other questions about this kind of fundamental change? It may not seem like a big deal, but it is a big deal when we're talking about getting into the details of how we do the code. Let's see here. And so part of this whole rewriting the 2017 code talks about functional grounding, and which is a different animal. The way to think about functional grounding is that it's not a solid wire to earth. A solid wire to earth is done for the purpose of what we call protective grounding. Okay? It's for safety purposes. The protective ground or protective earthing of a circuit is done with a solid wire, no overcurrent devices, no switches, no nothing connection to earth. Whereas with a functional grounding system, it performs functions that could have safety functions related to them, but they're not required for safety. So in the AC circuits, the National Electrical Code in general, we have circuits that must be connected to earth. It's a safety requirement because of the basic, just the way we set up our AC systems. It's one of the methods of an AC distribution system, and it's required because of the way we do it. Since the PV system is not necessarily part of the load system of a building, we can do whatever we want on the DC side of our inverter as long as it's safe. So we can set up whatever kind of network is appropriate for our system as long as it's safe and it's properly tested and evaluated. And the way we've been doing it since about 1990, the vast majority, if not all systems, have been functionally grounded through ground fault detectors that have got fuses or circuit breakers and things like that connected to earth. So that's a definition change, but it's really redefining what we've been doing all along. So 690.4 talks about multiple PV systems. Now it talks about, which used to talk about inverters, multiple inverters. So we're saying we could have multiple PV systems on a building, and if we do have multiple PV systems on a building, at each different location where the PV systems are actually connected to the building electrical system, we have to have a sign at that location, and it has to identify where all the other connections of PV systems are on that building if there's more than one. It's the same requirement as in Article 705. It's been there forever. It just is matching it up with that. and it's not related to inverters, it's related to systems. And so that we're going to put this at the PV system disconnecting means, wherever that PV system disconnecting means is, that's going to be the identification of the termination of that system. And if systems are at other electrical locations in the building, then it's going to show where those are. Article 690.5, which is ground fault detection, got moved to 690.41, which is the grounding section, to keep all the grounding stuff together in one place instead of jumping around. And then 690.7, which deals with voltage calculations and the definition of voltage, was heavily revised and reduced, cleaned up, and there's also three different methods now allowed for calculating voltage, which is a big benefit because one is the very simplest, which is the table. The second is the coefficients, which is what people become aware of since 2008 and worked with. And then the third is actually engineering calculations for systems over 100 kilowatts and allowed. So now we can do calculations based on simulations and even be a little more accurate, shall we say, in our calculations for larger systems that are under engineering supervision, which can help for sure. Let's go back, sorry. And in the same way, we have options for calculating current. The standard way we calculated maximum current on a PV circuit was the short circuit current of the PV module or string times 125%. Okay? Where did that 125% come from? I heard one correct answer. Radiance. It was all about radiance. Okay, the first 125% is saying your standard test conditions, short circuit current, is at 1,000 watts per square meter. But 1,000 watts per square meter is not necessarily the maximum radiance that you can get at any location. So, for a fudge factor, so you don't have to tell us where you are in the country or whether you're at 4,000 feet or whatever, we're going to give you a fudge factor of 25%. And we're just going to throw that in there. And we're going to throw that in there on top of short circuit current, okay? Because in the old days, we could have short circuits in an array, and those short circuits could stay forever without tripping over current devices or anything like that. And so we had to size our wire for that continuous operation in a higher radiance condition at short circuit. But then when we back the truck up and we say, well, wait a minute, our PV systems aren't made that way anymore. First of all, it's impossible to have an array operating at short circuit current continuously. And the fact is that there's a lot of systems that are roof mounted. For instance, a roof mounted ballasted system that's at a 10-degree tilt or a 5-degree tilt that'll never see 1,250 watts per square meter, ever, except maybe for a few seconds. And we're talking about, we're sizing conductors. This is a 3-hour period. Okay, so what this new provision in 690.8 covers is it allows for, again, engineering supervision for 100 kilowatts and up. So again, these are engineer systems where we can actually calculate through simulations very accurately a 3-hour period, what's the maximum current that we'd ever see at that site on those modules in a year. All right? And we can use that number. That number cannot be any less than 70% of the number that we've always used. Okay, there's a floor set on that. Okay, so it says, you know, the standard number of short circuit current times 125%, the number that you calculate when you do all this can't be any less than 70% of that number. Okay, and that's just to keep people from just trying to, you know, justify a number that's a third of the amp, you know, whatever, some crazy number that just doesn't make any sense. But when we're talking about larger systems, and of course this is only allowed for slightly larger systems, 100 kilowatts and up, this can be huge conductor savings because we're talking about 20 to 30% in the size of the conductor. 20 to 30%. Because we've been oversizing conductors on large systems for a decade now, a long, long time, way oversizing them. And back 10 years ago, it was no big deal, right? PV modules were expensive. Copper's cheap. Aluminum's cheap even. We went to aluminum because copper was expensive. But that ain't the case anymore. Our wiring systems are becoming a huge part of the cost of a PV system. And on a large system, we have to get those costs down, and we have to do it technically correct. So we're not saying just, oh, I like a number that's 80% of what I used to use. You got to do the calculation. You have to do the simulation. It's engineered, and the engineer has to sign off on it. And they have to know what the heck they're doing to do all that. But it does help justify the use of an engineer. And I would say that it's very rare for a system, even over 20 or 30 kilowatts, to not require an engineering stamp. Very rare. So 100 kilowatts, I haven't seen a 100 kilowatt or larger system without an engineering stamp on it in my memory. Never seen one. There may be a few out there, but not that many. Okay. So that's a little bit about current, and then 690.9 requires an overcurrent protection device in both the positive and negative of the array. We mentioned that earlier, and that's for safety reasons. It also works with any type of a grounded or ungrounded system. I'm sorry, the OCPD is the overcurrent protective devices in either the positive or negative, whereas, let me back the truck up, 690.35, which is ungrounded systems in the code, required that you have fusing on positive and negative, or on both ungrounded legs. Because of ground fault detectors, that's really unnecessary. The ground fault detector can operate and keep the system in a safe condition with only one overcurrent device. It doesn't require the second overcurrent device. So in our normal systems in the US, our two-pole breakers are circuit breakers, right? Because we get a fault on either one, and that side is going to trip the other side. It's a ganged breaker. But that's because we don't have any ground fault protection on our system, and that's why we need it. With ground fault protection, we only need it in one of the legs. And so because the circuit, the fuse will blow if it's called upon because of the circuit regardless. And so the circuit will never be will never see overcurrent when you have only one overcurrent device. So it's a waste of money and a waste of resources to have overcurrent devices in both legs, and so it's either in the plus or the minus, but you can't mix it up. So if it's either a plus fuse system or it's a minus fuse system, you can't have plus fuses on part of the array and minus fuses on another part of the same array. That's not allowed. That's a nightmare, and that's actually happened before, and it doesn't work real well. And then, as I mentioned, on the disconnecting means side, what we'll get in here, it actually requires disconnecting both the positive and the negative in 690.15. 690.10, which is standalone systems, got moved to a new Article 710, so all that text was just simply moved over with a reference. 690.11 is our arc fault section. Arc fault section of the code, as I said, went from buildings only to ground mount as well, and then in the 2017 code we put some exceptions in for ground mount systems. And those exceptions are that you do not have to have arc fault protection on PV output circuits that are either buried or in metallic raceways. So the output circuit does not required to have arc fault detection on it, but the source circuits still are required to have arc fault detection on a ground-mounted system. So it has to, one of the reasons and one of the justifications for it is that we really don't have any arc fault detectors that work at, or that are even built for larger, 100 or 200, 300, 400 amp circuits. They don't exist yet. And that's not the predominant place where we see our arc faults. The vast majority of the arc faults are on the small side of the system. So it gives a little breather to the ground mount world. for areas that are required to meet that. Now, when we talk about arc fault protection on large-scale plants, 691, Article 691 on large-scale plants says that if you're not going to comply with 690.11, that you've got to have some type of an engineered plan for how you're going to address arc faults in a PV array. And there are various ways of doing that. But as arc fault protection continues to mature, even the largest of systems will probably incorporate it regardless of the requirement. Rapid shutdown requirements are now inside the array in addition to outside the array, so we can talk about that a little bit as we finish up this afternoon. But the PV system disconnecting means is rewritten in 690.13. One of the things that, quite honestly, I think we've done a disservice in the code with is all the requirements related to disconnects are very hard to follow. They're convoluted. They originally started with requirements that were kind of cut and pasted from the service Article 230 for services, and they've been cut and pasted into PV, which has caused people to generally think of a PV system as a service. And a PV system is not a service. A PV system is a parallel power generator, parallel power source, and which is talked about in Article 230. And so it's really only a service from the standpoint of what we think of as electrical services in a standalone system where there's no other source. You could argue that that's, essentially that's the service to the building, but in general, it's an ancillary service to an existing power system. So some of that is terminology, but it's important that we get our terminology straight. For instance, here's an example. So the way that services are set up is that we have something that's been in 690.13 forever that says that the DC conductors coming off a PV array must have a disconnect either outside the building or the first point of entry into the building. Okay, everybody familiar with that? Heard of that before? So it says that if we're going to bring conductors from a PV array into a building, we've got to have a disconnect either outside the building or the first point of entry into the building. Well, that sounds like a service to me because it's the exact same language that's for services. All right. And then we put in a little exception that says that if you go in metal raceway, from the point of penetration, you can go all the way to the first readily accessible disconnecting means as long as you're in metal raceway. You don't have to have the disconnect outside the building or first point of entry. Okay, well that essentially bought us a little bit of breathing room because a lot of times we're going to bring our PV conductors in through the roof, right? So if you come through the roof into the attic, where are you going to put your readily accessible disconnecting means? Well, there's no, most attics are not readily accessible, things like that. So there was all kinds of issues. The roof is not readily accessible, so you can't put a disconnect on the roof and comply with that. So it was a bit of a conundrum. And so it's always been there, and we've kind of worked around it in different ways. Again, this metal raceway provision was a way of working around that. But a new thing came along, and it's called rapid shutdown. Now, rapid shutdown is seen by most in the PV industry as kind of a bummer. And, this is the fire service trying to, exert their whatever influence on the PV industry. And just want to share with you that this has been coming for a very long time. This is not a new thing, but it has gone into the code in the 2014 code. What that does require is that conductors leaving a PV array be shut down. Okay, so that brings up a really interesting thing. So now you're going to shut off the array, which is often going to have conductors going into the building. So cutting off the conductors going into the building was actually really the first and foremost concern of the firefighter. They wanted to make sure that if conductors were disappearing inside the structure, that those things were turned off somehow so that when they go in to rescue somebody, they don't have to be worried about shock, some crazy things going on with that. And so that was its first issue. So then we said, well, wait a minute. We've got a provision that says that you have to have a disconnecting means before coming in the building. Well, rapid shutdown is a disconnecting means of sorts. If we get credit for that disconnecting means, which we had to pay a lot of money for and deal with and and whatever we had to do to accommodate rapid shutdown, then we can put our PV system disconnecting means anywhere we want, right? Because now we have a means of turning the system off at the barrier to the building, so your building envelope is a very key, penetrating the building envelope is a really key thing for electrical work, okay? So we're controlling the conductors that penetrate the building envelope, but then the switch to turn that thing off might be in a service panel that's in the basement, right? Could be in a service panel that's in a utility room in the house or something like that, which is not at all accessible from the exterior of the building for whatever reason. And so anyway, but we can turn the system off. We have a PV system disconnecting means at a circuit breaker in our panel, and we have a means of actually addressing the boundary between the outside world and the inside world for a PV system. So that's some of the nomenclature we took advantage of in the 2017 code, so that we don't have this stipulation where we have to look for a disconnect either inside or outside the building, or look for metal raceways all over the place. So I said 690.15 deals with equipment disconnects. Now, equipment disconnects, it's been a fairly basic requirement in the code up to now, which has said, you got to shut off all sources of power to most equipment, and it lists a couple pieces of equipment. Unfortunately, that hasn't been real specific, so that's created some problems. So we got real specific on what equipment has to have disconnects, and then we differentiate between disconnecting means that are load break and disconnecting means that are not load break. For instance, a connector is generally not a load break device. Now, at very low voltages, a connector can be a load break device. In fact, the N-phase inverter has listed their product as a load break disconnect, their DC connector. And they've also listed their AC disconnector as a load break device. And so it's possible to get these things listed as such, but you can't say, I can't take an MC4 connector, for instance, that is listed for up to 50 amps. That thing can handle 50 amps. I can't put it in a 600 volt or 1,000 volt circuit and call it a load break disconnect, because it ain't close to a load break disconnect in that circuit, okay? It will be spectacular if you try to take it apart at 50 amps. And neither will the manufacturer support that, and they say specifically right on the side of it, according to 690.33e, it says, do not disconnect under load, all right? Even though it's actually been certified to disconnect under load by N-phase and a few other folks. So what we're going to see in the future is, in the very near future, in fact, I think you can walk outside and see HiQ's product right now is exactly the kind of product that we envisioned in the code, is that you have an inverter that has plug inputs into it, and that's it. There's no terminal box on a HiQ inverter. It's just a bunch of plugs. Okay, so we have two DC inputs that we can bring into that inverter. We got one AC cable output. There's a little push button on the side of it. We turn the thing off with the little push button. We unplug it, yank it out, throw another one in, plug it in, push the button, turn it on, and we're out of there. That's completely safe, and it should be allowed, and guess what? Now it is allowed, specifically. Now you could argue that you could still do a HiQ inverter under the 2014 code, because we have an exception buried in 690.17 that says that connectors can be used as a disconnect if they're used with listed equipment according to their listings and and that's how we justify microinverters, and most people have bought off on that, but the language in 690.15 is very specific now, and we talk about isolating devices. So a connector is an isolating device. An isolating device is one that specifically does not necessarily have a load break rating to it. That's why it's called an isolating device rather than a disconnect. Okay? A disconnect is something you can throw anytime, anywhere, doesn't matter, safety, for whatever reason you have to, you got to turn that switch. There's no stipulation on it. An isolation switch, in fact, utilities use isolation switches. And on a big generator, they'll have an isolation switch, and it's do not disconnect under load or you will find yourself across the room somewhere. The only purpose of that switch is after everything's been turned off, it creates a separation point that everybody's clear about. We got no connection. There it is. But it's never operated under load. And you double check and triple check before you ever open that switch, because your life depends on it. 690.16 through 19 is gone. If you had some of your favorite parts in there, too bad. They didn't belong in the code. Well, actually, we redistributed what was in 17 to 15 and 13. 31, basically, and this is an important issue, I think, and several folks have brought up questions about this over the last couple of days, is that the 2017 code, we want everything wired the same way. So there's not this, in 2014 and before, we have ungrounded systems, we have grounded systems. And ungrounded systems require fusing, positive and negative, require PV wire, multi-conductor cable, all this stuff. And we had to worry about all that, make sure your modules have PV wire on them and all that kind of stuff. And with an ungrounded system, because an ungrounded system is a less safe system, and we're worried about Class 2 European wiring systems, all these kind of things were flowing around related to that. And it's like, timeout, guys, something's wrong here. And we backed the truck all the way up, and I actually worked with some guys in Europe on this particular issue, and they go, guys, you do not want to classify your stuff as Class 2 systems. You don't need to do that. USE cable's just fine. PV wire is great. USE is great. Use them either, both, whatever you want to do. And so basically, all PV systems, whether they're grounded, ungrounded, resistive grounded, whatever, all get the same wire. You can either use PV wire or USE2, which is the way the current code reads. You're allowed to have fusing in one conductor. Okay, so that's a good thing. And then the only difference between the way we've been doing it forever and the way we do it now is that we require disconnecting means in the positive and negative leg. Now, on a lot of our older systems, we're using things like the square D disconnects and things like that. And what did we do? We went through the square D disconnect twice, right? Everybody familiar with that? Okay, so you had a square D, let's call it a 361, which is the 60 amp or 30 amp version, a 600 volt 30 amp version, 362, 60 amp, and on up like that. And so the inspector, I mean, we've been saying for years, okay, you bring in your positive conductor from your PV array, and you come into phase A, you put a loop around from the bottom of phase A over to phase C, and you come out phase C, and now you've cut the circuit twice, and that will handle 600 volts just beautifully on a square D HU361RB. Okay, great. Well, one of the other configurations of that very same switch is to put the positive on the left pole and the negative on the right pole, and that works too. Okay, you're cutting the circuit in two places at the same time, but one's the positive and one's the negative. And so you could rewire your system if you have those types of switches. That's a very simple thing to rewire, and you would be back in compliance with the code. And the reason all this is important to us is that a very big issue, which is becoming a more and more of an important issue now, is that we have legacy systems that were all wired in the old school way, right? And that legacy system, we got to figure out how are we going to wire it for the new system. Well, the way the code was written in 2014, we were a bit of a conundrum in that if we wanted to take a non-isolated inverter, which is the prominent inverter being used today, we call that an ungrounded inverter. The array is ungrounded when the system is not operating. It actually happens to be grounded when it is operating, but when it's not operating, it's ungrounded. So we called it an ungrounded system. And then now we're in violation of the electrical code because our wire's all USE2, right? That's the way it was installed, with all USE conductors. And so now we've got to go to the HJ and make an argument to them, and I've done this several times, where the new inverter that we're putting in, so we're replacing an old SMA Sunny Boy inverter that failed or whatever it is, and SMA doesn't have any fused grounded inverters anymore. They've used them all up. Okay, so the only thing they can say, well, hey, we can give you our latest and greatest inverter, and that's what we're going to replace your product with. Well, when you come to put it in, it's an ungrounded inverter, so do you have to comply with all those things or not? And so the reality is that an ungrounded inverter, the non-isolated inverters, are actually quite a bit safer than the unit you're pulling out of service in exactly the wiring configuration that you're putting it into. So you're installing it on an array that's configured for a fuse grounded system, negatively grounded, but with the exception of that darn negative leg that'll go hot when the system has a ground fault. That new inverter is far, far safer than the old inverter that came out of it because it's got a much better ground fault detector, and the new one's going to have an arc fault detector in it as well. So, any questions about replacing inverters, things like that? It's a big deal. I mean, how many people have had to replace an inverter in their career? You think you might have to do one again sometime? Maybe. Yeah, it's pretty much an assurance. And, you know, a lot of inverter replacements are just considered maintenance, and we just replace them. We don't go back and do any kind of permitting, and I'm okay with that. I don't think that's a big deal. There are definitely stipulations on when it really should be permitted, and there's examples where we're going to do any reconfigurations or things like that where it would absolutely require a permit. But in that gray area, whether or not a permit is required or not, it doesn't matter. It's important that it's safe. Is what you're putting in safe? Is it done properly? And the answer is, you know, with these newer inverters, the answer is basically yes. And I would say the only potential issue that I could even think of is that you have this warning on your inverters that says that ungrounded conductors can be, or grounded conductors can be ungrounded and have voltage on them. Well, it turns out that the ungrounded inverters have almost the same node on them, so I don't really see it as a big deal. Okay, 690.35 is gone because it's confusing, and it was giving two different ways of wiring things. Anyway, just kind of finish up talking about all these changes. 690.41 is where all this grounding stuff changed. And solid grounded systems are extremely rare. It's solid grounded systems where we have wire connected to our conductor only allowed for 1 and 2 string circuits or 1 and 2 source circuit arrays that are completely separate from buildings. So you're not allowed to bring those conductors anywhere near a building or in a building. And those are the only ones that are allowed to not have ground fault detection on them. So if you have a solidly grounded system, it's allowed to not have ground fault detection on it. But it's also can't have anything to do with the building. Cleaned up and simplified 690.43 related to equipment grounding and equipment grounding conductors and bonding. Completely revamped 690.47, and this was one of the bigger ones. We talked about earlier about this issue of grounding electrodes and things like that, how grounding electrodes have to be done in PV systems, or how are they done in all electrical systems. And there was just lots of words in there that were easy to misconstrue and get confused. We had DC grounding and AC ground, DC system grounding, AC system grounding, systems with both AC and DC, and it's like I'm getting really confused here. Wasn't helping anybody. And so what we did is bring it all the way back to basic principles, which is if you're going to put in a PV system, the structure that's holding the PV system has to have an electrode. Now, this is going to get to your question in a second here. Okay, so structure, so if you're putting it on your house, the structure is your house, right? That structure, if you have electricity already in it, which most people do, has an electrode. Okay, so you've satisfied the requirement. Okay, The structure you're putting it on has an electrode, and the equipment grounding conductor that's connected to that array is going to find its way to that electrode if all the wiring's done the way that we wire systems and we wire equipment. All right, so, and that's good. Now, if we want to do lightning protection, anything like that, that's a completely different game. Lightning protection is not part of the National Electrical Code. Okay, there is a section to Article 280 on surge protective devices. When we put them in, here's how you wire them. It is not a requirement of the code. If anybody tells you the lightning protection's a requirement of the code, they're lying to you and they don't know what they're talking about. Okay? Now, is lightning protection important? In some places, it's critical. In fact, you would be stupid not to have lightning protection. All right? Places like Florida, great example. However, it's not part of the National Electrical Code, and I don't think it's going to be part of the electrical code anytime soon. We have an NFPA standard called NFPA 780, which actually has specific language in it on how to address photovoltaic systems. So if you want to do a lightning protection system, there is guidance in NFPA 780 that tells you how to do that. But we are not going to put it in NFPA 70, which is the National Electrical Code. Okay? So we had this thing called 69047D about an additional array electrode. And when we boiled it all down, I put in the original proposal with John Wiles to require that all ground-mounted systems that were separated from buildings would have an electrode. Well, they took that and they wound it all around and they completely screwed it up, and they wrote, the code panel wrote 47D, which completely missed the point. We're getting back to that point, which is that if you're supporting PV modules, whether it's ground-mounted or whether it's on the roof of a house or a building, then that structure is going to have a grounding electrode conductor or a grounding electrode system. Now, you made the point that, hey, I've got 500 5-foot deep piles in the ground, and that's a really good connection to earth. And you are absolutely 100% correct. But the code doesn't recognize them as a grounding electrode system, which is a bummer. So in that particular case, it's really just a matter of, shall we say, technicality. I'm going to drive a ground rod anywhere I want at that structure, tie it to the structure, and now I have a grounding electrode. Does it do anything more than the 500 5-foot deep piles? Absolutely not. Does it have any improvement on the situation? Yes, it gets you through your inspection. Beyond that, it has absolutely no effect. But you can't argue this one. I mean, this is one of those things, the code doesn't recognize it as a grounding electrode system. If it's not a listed grounding electrode, it ain't going to fly, and if it ain't on the list, they're just not going to buy it. Now, some will. I mean, some will say, oh, yeah, don't worry about it, if they understand the concept. But how much does an electrode cost? Not enough to worry about this thing. Put the dang thing in the ground, move on with life. But we do want to have a local electrode, and we want to tie our equipment grounding conductor to that electrode. That's not the end of that equipment grounding conductor circuit. It's just making sure that the frames of whatever we're mounting the thing on are tied to a local electrode. Now, we still may be going 200 feet over to the house, and there's an equipment grounding conductor going with the circuit conductors over there, and it's going to be tied into the service panel over there. Okay? But we don't want to rely on the grounding electrode system of 200 feet away to be standing on, working on something without having a local electrode. It's just not cool.
So there used to, there was a section in the code in here that defined a couple of different systems of concrete in the ground or this or that. Yeah. That's essentially been pulled out.
No, still there. There's 5 different grounding electrode systems allowed in the code. They're all in there, but you're not one of them. So a pipe 5 feet deep with concrete around it is not an electrode. A pipe 8 feet deep is an electrode. Doesn't matter whether it's concrete or not. Could be concrete encased, doesn't matter. It's 8 feet embedded in the earth. That's the criteria that you're asking. So that's the one you've met. So you can have a U for ground, which is essentially embedded in a concrete slab. Ground rings. So these are all stipulations on different varying methods, but the easiest and simplest one is a driven ground rod. And as long as you can, if you can get piles 5 feet deep, you can get a ground rod 8 feet deep. So, so that's significantly cleaned up. And what happened with 47D is that the International Association of Electrical Inspectors, which brought back 47D into the 14 code and fought them tooth and nail on this to the point where it was almost embarrassing in the meeting. I mean, this is like, it was over my dead body, and it almost became that. It went back into the code. And so they tried to bring it back again this year, both sessions. Brought it back in the first one. And so I put in a proposal to get rid of the whole thing. And then we neutered it, and basically what we did is we said, okay, if you guys feel like these words have to be in the code somehow, this has to be a permissive rather than a requirement, because you could argue that it's dangerous to do this, okay? It's not right, and it could even be dangerous, so to do it the way that it was written. And they weren't willing to rewrite it, so if you're going to do it dangerous, you can't bring it back into the code. So we made it a permissive and said it's permitted provided that you follow these rules, which make it not unsafe. So it will be permissive moving forward, and hopefully the bummer, how many folks work in California? The bummer about California is that we're not on the 2014 code yet. And we've had this reprieve because it was taken out of the 2011 code. And now we're going to go back to it in the 2014 code. And so what we have to do is somehow get authoritative folks on board with the fact that the 2017 code makes it permissive, and so that jurisdictions don't start enforcing it. So they see the ambiguity of what's going on here, and they go, well, clearly the code-making panel can't figure this thing out, so let's just not do it. Because the only reason that it came back in the code in the 2014 cycle was because it was an error that it was taken out of the 2011 code. It's actually true. The fact is, I fought this thing tooth and nail that it shouldn't be in the 2011 code. They voted me down at the final meeting. It was 14-1, and the staff misconstrued the vote, and they thought they were voting in favor of getting rid of it when they were voting in favor of keeping it. It was just a miscommunication, and I was like, I don't mind that miscommunication at all. I think that was a pretty good one. Bank error in your favor. It's like, yes. So then they brought it back in the 2014 code on the basis that it was removed by accident. So anyway, that's the code. Lovely. 690, 60 through the end of the code of 690 is all gone, with a few references remaining. So we reference Article 705, we reference Article 706 for batteries, and we move all that stuff out of the code. So we're about, the good news, bad news is we removed about 3 pages of the 15 pages of Article 690. The bad news is that rapid shutdown brought back about a page. So, all right. Let's take a quick break. Okay, so we're going to finish up this afternoon, and do want to talk about the 2014 NEC with load side connections, and if we have some time after that, we can talk a little bit about rapid shutdown 2014 and kind of looking forward. So basically, in the past, really unintentionally, bus bars and conductors were listed in the same sentence. And we really didn't mean that as far as everything applying to everything, but because of that, there has been some very messed up views on how to size bus bars and conductors, particularly conductors. So what we did is we separated into feeders, taps, and bus bars. Each have different rules since they they have different characteristics. And so we need to have them separate. So the first one, basically, so 705.12d has 1 through 6. And it's pretty lengthy. And number 1 on this list of what it has to comply is going to a dedicated overcurrent protection, or overcurrent and disconnect. And the way it was written, and I hadn't really seen too many inspectors mess this up yet, but I saw it coming, is that it said the source connection shall be made at a dedicated circuit breaker or fusible disconnecting means, which is true, but I could see somebody saying, well, you know, that N-phase inverter you're talking about, that's really the connection for that, you can't connect it to a bunch of other microinverters. You have to bring it back to a circuit breaker every single time. And it's like, no. That's not what it's saying. It's saying when we make a connection to the rest of the world, that connection be done at a dedicated breaker. When we say dedicated, the word dedicated doesn't mean that we only have one. It means that there are no loads on that circuit. Okay, so we can't have, for instance, we can't come off of a microinverter system and then somewhere in that microinverter system we cut off to plug loads, to lighting and stuff like that, and then make it to our circuit breaker in the panel. That's not acceptable. We take that microinverter system, that circuit with 10 or 15 microinverters on it, and we run that to a circuit breaker, whereby in that panel then we can distribute to anything we want, because each one has their own overcurrent protection. And so that's really what it was intended to say. And so we said, well, since somebody could screw this up, we should say 1 or more inverters installed in one system, so that it was clear that multiple inverters could be installed on the same breaker. Now, a microinverter system is something that we all can relate to really well, but if you go out in the exhibit hall, you can see High-Q, and they've got 3 8-kilowatt inverters on one 40-amp breaker. How did they do that? Well, it's the same kind of idea. They got multiple inverters on the same breaker, just like a microinverter. The word microinverter is not in the code. Mini inverter is not in the code. String inverter is not in the code. The word inverter is the only thing in the code. So we don't differentiate on size. Okay, when we get into busbar or conductor ampere rating, the previous versions of the code use the circuit breaker rating for all the calculations. Unfortunately, with using the circuit breaker rating, that can create some problems, particularly for microinverters, more than probably anything else, whereby it's pretty common, for those of you who are familiar with doing microinverter systems, to have, let's say the maximum number of microinverters you can put on a 20-amp circuit breaker is 15. All right? But you may not put 15 on one. Maybe you have 3 breakers or 2 breakers, and you've got only 10 on one, and you got 15 on another, or 12 on one and 12 on one, and that can really screw you up when you're only allowed to have a total of 40 amps of breakers on a particular 200 amp panel. So what this says is that for all our calculations, we're going to use 125% of the inverter output circuit current for all our calculations. So now the microinverter, which has a 1 amp output, is really considered a 1.25 amp output for the purposes of doing our calculations, and we run our calculations all based on that for our maximum number of this and that and the other thing. And that keeps us from this thing called roundup error, right? So when you have roundup error, we're already being very constrained on this 120% rule, and the roundup error can take us right over that 120% pretty routinely. And so it's a little more calculation, but it's a lot more accurate, and it lets us put more PV on the same system. So we added feeders and taps, and of course we already had bus bars. So the first thing on feeders, so what's the definition of a feeder? So we get on the same page here. What's a feeder? So it's from a panel, so typically it's from the main service panel to a sub panel. That's a feeder. And typically we don't run loads on a feeder unless there's only one load on that conductor at the end of it. Okay? So typically a feeder is just transporting power from one location, from one panel to another panel. All right? So it says where the inverter output connection is made to a feeder at a location other than the opposite end of the feeder. So what we're saying is that we got a feeder, and it's starting at the main panel, it's going to a sub-panel. Somewhere in the middle, and we'll show some pictures of this, we're going to interject a PV system. All right? Then we have to address some problems that we've done by putting extra power in the middle of that circuit. Now, when it's at the opposite end, what happens? So now we've got our main panel over here and our sub-panel over here, and we connect right before we get to the sub-panel. We connect the PV system in there. Well, the current can either go this way, or the power can go this way into the sub-panel. Or if there's no loads in the sub-panel, the power can go this way back to the main panel. They can't go they can't go in opposite directions at the same time. And the feeder only has to be sized for the larger of those two calculations. Okay, so let's look at this, understanding the opposite end. So if we're back over here, if our PV system's way over here, then we don't have to upsize this conductor at all because it's already sized for 200 amps. All right? Our inverter is actually only putting out 160 amps, so we have to size it up from there. And so it may be coming out of a 200 amp overcurrent device. And, and we're good to go. Now, this panel over here may have been a main lug only panel because the feeder breaker covered the loads in that panel and would protect the panel in normal. So if this happened to be a main lug only panel, then we would have to install a 200 amp breaker in here. And why is that? Because we got two sources, right? We've got a 200 amp breaker here and we got the 200 amp of the PV here. The wire between the two is just fine, but the bus is a problem. So the breaker protects the bus. Whether it had one or not, we're going to have to put one in. Then we're going to talk about taps in a minute, and now we have a tap off of this thing. How do we size that? And we'll talk about that in a second. Feeder ampacity should not be less than the sum of the primary source breaker and 125% of the inverter output circuit current if you're feeding it from one end. Okay? Secondly, we can put an overcurrent device on the load side of the inverter connection and shall be rated for not greater than the ampacity of the feeder. So what we do here is go, well, okay, now let's move that PV system from here and let's move it to the middle. All right? There's nothing wrong in here for the 200 amps. There's no more than 200 amps can flow in this part of the circuit right here, right? Everybody clear with that? It's either 200 amps from the utility or 200 amps from the PV or something in between. There is no way to get more than that. But this section of conductor here that's in green, which probably shouldn't be green, it should be red, is going to be, in order for this to work, you'd have to have a 400 amp bus and you'd have to have a 400 amp conductor. Okay, the probability of that's really small, but that would be one way to address it, would be to upsize those downstream conductors. Okay, so that's A. That would be complying with A, is to upscale this to 400 amps and have a 400 amp panel. The easier and probably the most likely way you would do that is to actually reinstall the feeder breaker or relocate the feeder breaker for at the connection point of where the PV system comes in. What this does is maybe somewhat obvious or maybe not obvious, that it protects everything downstream so you can flow no more than 200 amps on that portion of the circuit. This portion of the circuit's fine. This portion of the circuit has to be protected. Therefore, if people overloaded this panel for any reason, then this breaker would trip and protect everything downstream. Now, we could put it in this panel over here, but some wise ass could come along and argue that what if somebody taps this conductor in here and brings some extra load in here? So by putting it at the junction where we bring the PV in, since we're already going to have to do a bunch of electrical work at that point anyway, to interject yourself into a feeder is not a simple task. You're going to have to be doing a lot of electrical work in that area, so installing a new circuit breaker in there is not going to be that big of a deal. And we're doing it because it's saving us tons of money about doing it anywhere else in the system. We're saving money. This is all about trying to figure out the cheapest way of getting a pretty large amount of power into this building. And it just so happens that the best place to bring our conductors off the roof and into the building is right in the middle of this pretty nice size feeder, a 200 amp feeder, and now I can install it in that feeder and do it correctly without any safety hazards, and I'm protecting the downstream loads by this breaker. Any questions about that? Does that make sense? Okay. Now, what some people have said over the years is that, well, taps screw up everything because you have to worry about the extra source power from the PV, and that's going to add to the utility, and so now you're going to actually have, your taps are going to have to be sized greater than the size of the feeder. And people have said that. And it's like, what are you talking about? That's just crazy talk. That doesn't understand what taps are. Taps are always smaller than the feeder, and we're worried about, in a tap, we're worried about whether it can handle the fault current that could occur on that tap before it ever makes it to the overcurrent device. Okay, so taps are sized based on the size of the feeder breaker and the length of the tap. So Article 240.21b talks about 10-foot tap rule, 25-foot tap rule, and then exterior taps. Okay, taps outside of a building. So what we did is say, okay, to be super, super simple from the standpoint of you don't have to take off your shoes or make a big argument about it, we'll just say that the PV output is adding to the feeder breaker and that the sum of those two have to be used in the calculation. The ampacity of the wire doesn't have to match that. It's just your tap rule says that if you're 10 feet or less, then you're 1/10 of the ampacity of the feeder breaker. If you're 25 feet or less, then you're 1/3 of the ampacity of the feeder breaker. And what we're saying is that the feeder breaker doesn't calculate any current coming from the PV, so we just say if you've got a 200 amp feeder and you got a 200 amp PV, that it would be just like connecting to a 400 amp feeder breaker. And do all your calculations based on that. And that's going to be way better than not doing it at all. Okay, so let's take a look at that. Let's take a look at a scenario here. So the largest allowable PV system on the load side of a 1,000 amp service. So we're going to use a 1,000 amp service. We've got a 200 amp feeder. We're going to have a 9-foot tap with 100 amp. It's got a 100 amp tap to a 100 amp panel. The largest PV system, 200 amp connection, size governed by the inverter output. Is this okay? So let's look at that. So going back to the same diagram here, we've got this tap here. By definition, the tap overcurrent device is not at the tap location or where it taps into the feeder. It is 10 feet away from that location. That's allowed. And the size of this tap conductor can be no less than 1/10 of the feeder breaker. That's the normal way. So if we take PV out of it, let's just say the PV is not in the circuit at all, then the minimum size of this tap conductor would be 20 amps. That would be the minimum size before even looking at loads. And then we look, oh, I've got a 100 amp panel there. So the minimum load is the greater of the two, whatever the load is, or 1/10 of the feeder breaker size. So clearly the 100 amp way overrules that. Now we're going to say when you bring PV into it, it's like having a 400 amp breaker here, 200 plus 200. 1/10 of 400 is what? 40 amps. And then it would be the larger of the load, or 40 amps, which it already is at 100 amps. And so you're good to go. So your short tap conductors are going to be nothing to worry about. There's no way that a PV system is going to interrupt that problem or that issue. So let's talk about the 25-foot tap. So now, with the 25-foot tap, we've got to go to 1/3, and it's 1/3 of the feeder breaker plus the PV, and that creates a little bit different story because the tap is longer. The minimum ampacity of that conductor is not 100 amps. What overrules is 400 divided by 3, which is 133 amps. Okay? Now the likelihood that that 25-foot tap is already 133 amps is probably small. You have to calculate it, see what the ampacity of an existing conductor would be, and if it was not acceptable, you would either have to upgrade that tap to 133 ampacity conductor, or you would have to move. You would actually, the simpler way to do it would be to put an overcurrent device right there, within 10 feet of the tap. Because if you're within 10 feet of the tap, then the 10-foot tap rule would govern. So again, these are all trying to look at ways. The reason this was put into the code is the code is all about loads, and it's not about supply. It's not about, other than utilities. Article 705 is the first place we've ever dealt with this issue of mixing loads and generation in a building, in the building. Doing it at the service entrance, done all the time. In the building, not done all the time. It has to be, we have to use the right principles, and the right principles have to address two very important things. One is ampacity of conductors, so we don't overdrive any of the conductors that are in the building, burn somebody's building down. And the second is dealing with fault currents. So fault currents, when you have a fault happen, that everybody, all the circuit breakers do their jobs and doesn't create a fire hazard in that way either. So taps and feeders are all addressing both those overload and the fault current conditions. So I know this is a lot of stuff, but if you're working in small commercial applications, you are going to run into this stuff all the time.
So in these situations, you're saying you have 200 amps of PV? Is that what we're...
That's right.
So if you had a, on the left there, that panel, if it was less than 1,000 amp bus, you couldn't do it.
You couldn't do it. So the way the code is written is that the size of your PV cannot exceed 120% of any bus bars that it comes in contact with in the process. So the first thing to look at is how big is the service entrance and how big is the service bus bar. Because the way the code is written, if I got a 1,000 amp bus, I can't, if I have to go over 200, I'm going to a supply side connection. There is no two ways about it. There's no way in the code that I can do it any other way. Okay? If I could replace the main panel with a larger panel and downsize the main breaker and do all that kind of stuff, but on 1,000 amps, that's a big animal. That's a lot of money. So if I got an 800 amp panel, then you just do the math and keep backing yourself down. If I want to do a load side connection, the 120% rule is going to govern me wherever I hit, and all panels that I go upstream into have to comply. Okay? And so if I've got two levels of sub-panels, that makes it more complicated, because now I got to look at the next panel, and then I got to look at the next panel after that. And that's the way the code's written. Because here's a great example. I put in a system over here, and it's covering some parking that I've got over here on this side of the building. The electrical service for the building is 300 feet away on the other side of the building. Okay? I want to put in a 100 amp PV system there, and I got a sub panel sitting on that wall right over there. All right? I can come in, hit that sub panel, done. Otherwise, if I do a line side tap, I got to go all the way to the other end of the building. And that could be an enormous amount of money. And that often kills projects. I mean, so a lot of what we're talking about here is actually trying to save projects that where the numbers are already tight. We need to have good ways of connecting to existing electrical equipment that's totally safe and that everybody understands that it's safe. And the code historically has been oversimplified. The 120% rule, that's all anybody can think about, and they apply it to everything. They don't even know why they're applying it. You're talking about applying it to a transformer. What the heck? This is crazy talk. It's clearly losing perspective on why it's even there in the first place. Okay, so let's look at this particular scenario. If you had a 200 amp panel on a 200 amp feeder, you couldn't just interject it in the middle here because of, as we said, you could start loading up this main lug only panel, and essentially the PV breaker, the PV system could mask the main breaker from tripping that.
Any arguments to be made to a utility or jurisdiction saying commercial, that you can only make the connection at the main panel or near there because they want a PV production meter right next to the main panel?
Yeah, there could be all kinds of other reasons, but you know, when you're talking about a PV production meter, why does it matter where it is?
Some of the one cell connections made right there, and that's where they require it, so Roseville Electric as well.
So, but you've got an electronic meter, okay? So why does it matter where that electronic meter is even located? Now, if they need to have access to be able to read the meter, okay, well the meter itself could go there, but the electrical connection to the meter could be, I don't know, wirelessly sent from the meter module that's sitting on the other end of the building.
There's a lot of California jurisdictions that belong to the Modesto Irrigation District, all the ones there as well. You have to make the connection at the main panel or at a tap made at the main panel.
And the answer is they're injecting themselves. It's not a code issue. That's a local jurisdiction requirement. And quite frankly, on smaller buildings that are not spaced apart a lot, you know, that may be not a big deal. It may not be that big of an expense to go that further to the main electrical panel. But I can say that it's completely unnecessary to put those stipulations in because the technologies are there to put all the meters where they want them, but have them bringing that information from other places.
One of the schools, they wanted to do carports, and there was a panel they could have tied into. No, you got to trench all the way to the main panel and the main.
And it's going to take education. The answer no is simply, to me, is just work harder. We're not done yet. I don't stop at no, because if we stopped at no, we wouldn't be doing this today. We would have stopped a long time ago. We got no 30 years ago, 100 times, and 1,000 times.
In the PV program handbook, this is how thou shalt do this.
Exactly. And it's like, that was then, this is now. We got to rethink this stuff. And so.
But we still back to the solution that we have to have the disconnect within 10 feet of the main panel.
Right. Now that's a different story.
But it's still the same scenario, because we talked about using the sub panel that's over here instead of doing a line side tap that's way over there. You still have to get back over there.
Right. Now, and so that's probably a better example of something that you might have to deal with. So now the utility says, I want to have a visible load break, a visible break to your PV system on the property. Okay. Well, we use the pull-out meters in residences because those actually do that for them. And PG&E and others have accepted that. So how would we address that particular concern in a situation like this? One way is to have an external disconnect. So in this particular case, what I would sell to them, and I've done this before with SMUD and others, is that I'm going to put your utility disconnect right on the outside of the building right there. You have full access to that. And at the service entrance, you're going to have a sign, just like Article 705 says you have to have a sign. It's going to tell you exactly where that disconnect is. Okay? The code does not require it to be grouped. That would be a utility requirement. The utility requires a visible break switch, and I gave it to you in an accessible location. That's fully compliant with the code, or fully compliant with the utility requirement, and fully compliant with the code. And so the answer is not always no. The answer is here's the way of compliance. Grouping of connections together, utilities routinely feed large buildings from multiple services. Okay, large industrial facilities often have multiple services into the building, and for reliability and different reasons, and there's signage on those things, and they tell them how to shut down in a coordinated manner and stuff like that. So, you know, again, the cost of these things is very important, and the reason we have all these different options, or looking at all these different options, I just gave you one example of a situation where they're far apart, but there may be other reasons why I don't want to get into that 1,000 amp panel. Okay, making a connection in that 1,000 amp panel, maybe I don't have room in the panel, there's no place for conductors to fit in there, and it's not that I'm having to go a long distance, I just need to cut into the feeder. So.
Is there any considerations for sizing those conductors either in the line side or the load side like this, the sizing our conductors coming off our inverter? I mean, you could have a situation where you're feeding, you know, a 30 amp inverter into a, you know, we've had one actually, a 1600 amp bus or whatever on the load side, and those conductors could be, you know, running a long length through a building or whatever. So now we have a, you know, number 6, number 8 conductor connected to a, you know, a 1600 amp bus. Is that a
So the good question to that is the code's going to require you to have an overcurrent protection device at the point of connection in that case. It's not a tap.
Where is that at in the code? Which,
we just talked about it. Article 705.12D1 says that your interconnection must be at an overcurrent device.
see, and is that only for load side though? Because in D it says load side, but I didn't know.
So it's a load side connection, okay? And so if you're going to go supply side connection, so let's just go down that road. So if you're saying I want to put a 30 amp PV system into a 1600 amp panel, okay, then 705.31 says that if you got to have an overcurrent protective device within 10 feet of the connection. Okay, this is the first time, the 2014 code is the first time it says this specifically. The overcurrent protective device has to be within 10 feet of the physical connection to that bus, or if it's further than that, you have to put current limiters at the physical connection. So that would cover it. Okay? Now, I'll go into a brief rant about AIR ratings or AIC ratings, ampere interrupt ratings of equipment. So a lot of jurisdictions, in fact, I'm working with the city of Ontario right now here in Southern California, is they want to see ampere interrupt ratings on all the AC equipment, okay? And then occasionally you'll get them say, I want to see an ampere interrupt rating on your inverter. Inverters do not carry ampere interrupt ratings, okay? And if I have anything to do with it, they never will. Because I think it's a misconstruing of the way the code should be written. The overcurrent protective device that's upstream of that inverter must have the correct ampere interrupt ratings so that if the inverter faults, the circuit breaker opens every single time. That's there for protection. Because the breaker is what saves the world, okay? Not the internals of the inverter. The internals of the inverter are purposely shorted in the test, okay? It's the breaker that does the protection. And so in the case of what you're talking about there, you got a 1600 amp panel, and I want to put a 30 amp circuit breaker on that 1600 amp panel, because that would be the easy way to do it if I could. If I could just put a circuit breaker in there and connect it, well, that circuit breaker is going to have to be rated for the ampere interrupt rating of that service. So it's going to have to be a pretty beefy 30 amp breaker, okay? And then running the wires from there across to the other end of the building doesn't matter. If there's a fault, boom, that thing's going to trip, and it's not going to burn the building down. So, so that's also, it could be a fusible disconnecting means. So we could put a fusible disconnect in there. What the benefit of a fusible disconnect is, if we do it within 10 feet of the connection point, is that it can provide us our visible break for the utility. We can actually, if we can locate it carefully, we could put it on the outside of the building, and so have our visible break, fusible switch, good for 200,000 amps. It doesn't matter. I don't even have to think about what the short circuit rating of that service is. That thing's got an enormous ampere interrupt rating, and then I can go to wherever I have to go to pick up the inverter from there, whatever the current is. So, yeah, if you ever see somebody raise the issue of the ampere interrupt rating of an inverter, point them to the circuit breaker. And they may argue with you, and they say, well, I believe I'm right. So, unfortunately, what's caused us some problems is that the motor drive world, which, you know, a variable speed motor drive is basically, our inverters are just variable speed motor drives with different programming. That's all they are. The IGBT bridges that we're using in all our inverters come out of motor drives. We don't make PV inverter IGBT bridges. They all come out of motor drives, and we just drive that thing differently. Instead of a variable frequency, we're keeping a constant frequency, and we're varying power. That's all we're doing. So anyway, but the variable speed motor drive world does have ampere interrupt ratings on their equipment, and I believe they did that. They did that because a bunch of people gave them pressure. And now they do all kinds of testing on them when the breaker's the thing that really matters. And so there's going to be continuous pressure on forcing inverters to do the same testing, but that testing is expensive, and I believe it's unnecessary. It's covered by the breaker. Okay. So bus bars, either the bus bar is capable of handling all sources of supply, including solar and PV, with no limitation. That's what that first one is all about. Or the B on that is that you use the 120% rule, which restates the 120% rule from the 2011 code, and basically it only applies to bus bars, so it's clear that conductors have nothing to do with it, and then talks about the opposite end. The question in the back there?
Yeah, I was just going to ask, did they, when you said bus bars, did they put anything in the code about center fed?
Yes. Well, that's in the 2017 code. So, yeah, in fact, right before our session this afternoon, I was sending an email to one of our panel members. We're right in the middle of voting on the 2017 code. And one of the votes that's close right now is center-fed panel. So I put in a proposal to exempt center-fed panels on 1 and 2 family dwellings, center-fed panels, to exempt them from the opposite end of the bus bar rule. Okay? It was accepted with a majority and with better than a 2/3 majority, and we're about a 3/4 majority, but I'm nervous. And I don't want anybody to change their vote, for one. And there's a couple people that voted no that I didn't believe gave a good explanation as why they voted no. And I know them pretty well, and so I'm like, could you really change your vote to affirmative with a comment instead of no? Because I don't want this thing to go down. So we'll see what happens. But right now we're at about a 3/4 approval on that particular provision. And all it is an exemption for center-fed panels on dwellings, which essentially returns the code back to where it was before the 2005 code. Because if we look at the exception that was, the 120% rule was an exception. It wasn't a rule, it was an exception that was put in 1987. All right, it was put into the code to allow us to put in a 20 amp or a 40 amp breaker into a 100 or a 200 amp panel and not have to screw around ripping out the panel and doing all that kind of stuff. It was for residential only. It was an exemption or exception that was restricted to dwellings, and that thing lived there until the 2008 code, where we expand the 120% rule and made it a rule to commercial. And when we did that, we said, well, we got to have a good explanation as to why it could work for commercial, because commercial panels are generally more heavily loaded. So we said, well, if we put in a stipulation that the breaker has to be at the opposite end from the utility feed, then it'll prevent us from ever having an overcurrent on the panel. And that got through. Now, we thought we actually won it on that one, but turns out we didn't. But we got it through, and now we're able to do a 120% rule on this commercial panels, which is a big deal. Makes it a lot easier to make connections. But now we're going back and trying to fix this problem because Mr. Wiles raised the issue in an article. It was never brought up until he wrote that article. And we have had over 1,000 panels in the state of California alone ripped out. Brand new panels, many of them, because of that article. And it has nothing to do with safety. So we're trying to turn this all around, and it looks like it's gonna go through. And as soon as it goes through, the city of San Diego has agreed to actually make it a policy that they're not going to enforce center-fed panel replacements anymore. Oceanside, a bunch more. So we'll knock the dominoes down after that. Okay. So here's a, now the last one we're going to talk about here, okay, this is just the 120% rule. And so we've got a, let's see, this is actually the sum of the branch circuit breakers used to protect the bus bar. So, so we have the 120% rule, and I think everybody understands that. We got 200 amp from the utility, and it's a 200 amp bus. We could put a 40 amp PV breaker in that. Everybody gets that. So, but what we never had before was this thing called an AC combiner panel. Okay, so an AC combiner panel, which is bringing together essentially a bunch of different inverters into a single panel to a single feed that goes on from there. And so people were trying to apply the 120% rule to that combiner panel, right? And so you had a 200 amp feed from the utility, you had 200 amps of PV breakers in the panel, and we were upsizing it to 360 amps or something like that, which meant you had to go to a 400 amp panel in order to combine 200 amps of PV. And it's like, well, you only can have 200 amps of current flowing in here, so what's the deal? So to make it super, super simple, we said, okay, listen, think of it this way. The way we protect most distribution panels in the United States is we have a main breaker that's set at no more than the rating of the bus bar. All right, it could be less, but it can't be more, right? Everybody clear on that? We have a 200 amp panel, 200 amp bus, got a 200 amp main or less. Everybody's clear on that? All right, so now we go and say, well, wait a minute. What if I only had 10 20 amp breakers in a 200 amp panel? Would it matter what the main breakers was? Would it? If I have 10 20 amp load breakers, that's a total of 200 amps of load breakers that you're able to pull off of that. Do you even need a main breaker? Because the main breaker is not having to protect anything. There's no scenario, even if all the circuits were to operate at full power, that the panel could be overloaded. It's impossible to overload. Okay, so we said, well, that's what we're doing, right? We're putting a whole bunch of breakers in, and these breakers are typically run at full power, and we don't want more than 10 20 amp breakers in there. We don't need any more than 10 20 amp breakers in it. We're not asking to put more than 10 20 amp breakers in it, so why not protect it by the sum of the branch breakers, irrespective of what the main breaker is? And so that was what we got through with the code panel. So now if you have an N-phase system and you could have 10 20 amp circuits going to 10 N-phase systems, you could do it that way. We also said irrespective of load or supply, because we may say, you know what, I really don't need 10 20 amp breakers for the N-phase. I only need 9 of them, and then I'm going to have a 20 amp breaker or 15 amp breaker for some plug lows, and I'm going to plug their envoy in and do some other things in this panel. I need a little bit of load there. So, let's make this super simple so that nobody gets confused. You sum up all the breakers. As long as the sum of the breakers is equal to or less than the bus bar rating, you're good to go. Okay, and so now we have in the 2014 code the entrance of the AC combiner panel, which people have been doing for years, and in fact AHJs have been approving for years. But unfortunately, we've had a lot of experiences where AHJs have been doing the 120% rule and essentially upsizing, not quite doubling the requirement for the size of the panel. Okay?
So in reality, we're seeing panels that has far more than 200 amp if we added all the breakers up. Because in reality, that's what we're seeing out there.
That's a typical panel. And you don't protect that panel. As soon as you go to one breaker, 1 amp greater than the bus bar rating, you don't protect the panel that way. Okay, this is only specifically for...
Then they go back to, well, we don't use all 12 lights at the same time in our refrigerator stove and our dryer, you know, so they're all not.
We're not going to confuse people with that stuff. This is super simple. This is not a load calc at all. This is, we either protect a panel by the main breaker, which is set at no greater than the bus bar rating, or we protect the panel by the sum of the load breakers. One of the two. And if we do it with the sum of the load breakers, then we are required to put a sign on it that says, this panel, you're not allowed to add anything more than the sum of the load breakers, you know, of the bus bar. Okay, so you got to have this warning here. Let's just go back and look at that. This equipment fed by multiple sources, total rating of all overcurrent devices, excluding the main supply overcurrent device, shall not exceed the ampacity of the bus bar. Okay, so that warning sign is going to be in there. And so now we have, in this case, 430s and 240s equal 200 amps. Okay, they could be all utility interactive inverters. They could be utility interactive inverters and loads, actually something, and loads, or they could be, you know, so it doesn't matter. Any combination whatsoever. Okay? As soon as you put in one more breaker than what you see right there, then you got to do the 120% rule. You're done. And you're ripping that panel out. So, again, these are options. These are not saying you have to do it. That's why we're saying here's 3 options on how to do it this way, 3 options on how to do it this way, 3 options on how to do it this way. Because you never know what you're going to run into when you get into a building and what all the challenges are. And you can say, if I could just get the local jurisdiction to agree to this, it's perfectly fine. That's going to save me $2,000 or $5,000 or $10,000. So these can be huge savings. With ripping out equipment, it's using the existing equipment that you got. And then the last item here is multi-ampacity bus bars, center-fed panels. So connections, so the way the 2014 code is written is that connections to center-fed panels could be done under engineering supervision. So we have a bunch of jurisdictions in the state of California right now that if you get a letter from an engineer, they're okay with it. You know, that's really not ideal. It's better just to exempt it. So, but that provision is in the 2014 code, and we'll definitely see.
You're saying if we go upstream, every bus that we come in contact with would be required to have the 120% rule looked at it.
Upstream, not anything downstream.
So, does the rating of the meter socket also come into play with regards to the?
No.
So, like, if for the example before, for whatever reason, the meter socket was only rated at 800 amps, would you be limited in that respect?
So, yeah, that's a great question. And this is the crazy talk that we hear people talking about the rating of the meter, the rating of the transformer, the rating of the conductors coming in from the utility company. What the heck are we talking about that stuff for? It's not in the circuit. The current either comes from the utility or goes to the utility. It doesn't go at the same time. How can you add these things together? Let's be clear. The only time we can add things together is on a bus bar, where everybody's feeding into this big thing, and that's the only time we talk about the 120% rule. Period, end of discussion. And that's why the previous codes were confusing. I understand the confusion. We didn't say it quite right. We kind of were lazy in that way. So now we say it right. Bus bar, the 120% rule only comes up when we're talking about bus bars. And when we're looking at how much current we can flow on conductors, we look at the current flowing in one direction, look at that number, we look at the current flowing in the other direction. Whichever is the higher of the two is the size of the conductor. End of story. Okay? Just to give you one more example of this, and we'll get your question or comment, is that we do the exact same thing right now with standalone systems. It's in 690.10. It's been there for 4 code cycles. What it says is that we have an interconnecting breaker to the utility on a standby, on a backup system, right? That's a 70 amp breaker, let's say, a 60 amp breaker. Well, the inverter only can put out 25 amps. Why do we have a 70 amp breaker connected to the utility? Come on, battery backup people, tell me, why do I have a 70 amp breaker when my inverter only can produce 25 amps?
charge the batteries?
To charge my batteries, because I've got loads on the other side of that thing, and I want to be able to run those loads plus charge my battery at full power. And that means I got to have a big old breaker on that thing, all right? But that's the breaker that the inspector is going to look at in the 200 amp panel, and they're going to go, ho, 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 40 amps is all you get, buddy. And you got a 70 amp breaker there. You're going to have to downsize the main breaker. And it's like, no, you don't. The code says in 690.10 that the size of the back feed of the inverter is what's used for the calculations times 125%. And that's why we made it for everybody the same way, because it's just like connecting a 35 amp breaker to that panel for back feed, and it's a 70 amp load breaker and a 35 amp supply breaker. Just like our examples we had here with a sub panel. Go back to our little sub panel examples. Okay, I could have a much smaller PV system out here, right, and connect it to a 200 amp sub panel. That doesn't make this a 200 amp supply breaker. The code says the connection of the inverter breaker, that connection is used for all upstream calculations, not this guy. And it specifically says that for that very reason, because I might have a 40 amp breaker at this panel over here, and the 120% rule works fine on that, but I'm not going to call it a 200 amp breaker when I get to here. It's still a 40 amp breaker connected into this main panel. Does that make sense? That's the way the code's been written for 4 or 5 code cycles. So all we're doing is we're doing the exact same thing when we're talking about this issue of current coming in one direction versus current going back in the other direction. Okay, I have a 200 amp service, and so that has to be able to handle 200 amps of current, and I can push 40 amps of current back the other direction. Which is the bigger one? We've got bright people in the room. Which one's bigger, 200 amps or 40 amps? 200 amps. So guess which size you use? You use 200 amp conductors for your meter socket and your main and all that kind of stuff. The 40 amps doesn't change that at all. Now you try to put a 300 amp PV system on that, you got a problem, right? 300 amps versus 200 amps. Now everybody's got to upgrade to 300 amps. You got to have a 300 amp service minimum. All those things apply, because that's the bigger of the two.
On the center fed panel exemption, is there a requirement to still locate the breaker as far away from that center fed tap as possible, or can that be anywhere in there?
It says that it has to be it can be at either end, but not both ends.
And do you want to put the bigger breakers in between if possible? You had the choice on which one to go to?
The more heavily loaded side of the panel is the better place to put the PV. In general, that is the topmost space. I've looked at all those. When I did the research on this, I looked at every single center-fed panel on the market, and you put the big double pole breakers in the bottom, but those don't get run a lot. The ones that run all the time are your branch circuit breakers on the top of the panel, the single pole breakers and all that, and they're the ones that are more heavily loaded. And so if you really want to cool the panel off, you stick it at the top, but it really doesn't matter.
I've seen a couple big ones at the bottom feeding sub panels, and the guys putting in different things. So.
Yeah, put it wherever you think it's going to do the most good. Yep.
Back here. Yeah, real quick on the battery backup one, the radiant inverter, it's an 8,000 watt, and if you look at it, it said maximum AC current 33, which takes it over 40. But they pointed out, we pointed out, they've updated their spec sheet to know that the grid interactive current is actually only 7,200, so we can land on the 40 amp breaker.
Right. So, yeah, I mean, we've had problems for literally decades with inverter manufacturers putting in their literature current ratings that put it right over the breaker rating on us and screwed us really bad. And it's just ignorance on the part of the manufacturers. I'm sorry. There's no other way to say it. Do not screw us with your current ratings. I don't give a crap whether you can actually do 33 amps. I only want you to do 32 amps because that'll fit on a 40 amp breaker. That extra amp does no good to me other than make it so I can install it on this service. That's all it does. So if you see that, make sure you, and this is the feedback that knowledgeable people like you guys have to provide to your manufacturers, because these people are clueless at times. Present folks here accepted, but the fact is there's a lot of clueless people in the manufacturing world, particularly.
Sales and marketing people that want to get bigger.
Yeah, bigger is better. I was just thinking about that yesterday. I know we got to go, but I don't think they make small men's anymore. That's just, there's something wrong about that, a small man. I can't buy a small men's jacket anymore. It's got to be at least medium. You just can't do that. You can buy small ladies, heck yeah. Small ladies. Small ladies is culturally acceptable. Small men, that's kind of endowment issue going on there. I don't think that's right. So, yeah, marketing departments do all kinds of really strange things, and sometimes we have to set them straight because their best intentions are screwing us in the field, and that's not a good thing. So get, make sure you close the loop and say, guys, I know why you're doing this. And we're having issues, with stuff coming in from Asia and all this kind of stuff. These guys don't know anything about the code. They're coming in completely blind, and they're copying all the same mistakes of all the literature that's existing out there because they're just copying it. And they're like, well, these guys say 33 amps is the right number, so that's what I'm going to put in my thing. It's like, So give them the feedback. I mean, it's really important. So thanks, everybody, for hanging out. Let's go have a beer.